In section 5.3.1, we are going to begin to talk about the most awesome idea in all of calculus. And it actually comes in two parts. This is called the fundamental theorem of calculus. Now, the first part of the fundamental theorem of calculus is very, very strange because it is going to deal with a type of function that you have never seen before. If you take a look at this function, notice a couple things about it. First off, it's a function that's called g, and it has the variable x. And then when I look over here at the right, this is the really messy formula that contains x. And you'll notice the formula for this function is a definite integral. So we have never dealt with a function like this before. The variable of my function, you'll notice, is actually this upper limit of the integral. So if I was to say, try to find g of 1, then the value 1 would just go up here in this integral. If I wanted to find g of 10, then 10 would appear as this kind of upper bound. So this is a really strange looking function. If I wanted to start to figure out what exactly this function does, I would have to actually go ahead and select a specific function to take the place of f of t and a specific value to take the place of a. So let's go ahead and take a look at maybe one instance of this. So how about we go ahead and let f of t just be equal to a simple function, maybe like t. Okay, so this is kind of like a y equals x function, right? Very simple. And let's suppose that a is just the value of 0. Well, then what we would have is that our function g of x would actually look like an integral from 0 to x of the function t dt. So when I look at what this is really telling me, I can notice that g of x is a function that measures or calculates the area under the curve f of t equals t on the interval from 0 to some unspecified value of x. So if I was to say, try to take a look at this picture, I could see that if here is my t-axis, and here is my f of t-axis, and if I sketched the curve f of t equals t, that would produce, again, a line that kind of goes straight out from the origin like this. And if it's the case that x is going to be some value again that I can plug in, like let's suppose that x ended up being the value of 2, well then what I would do is if x was the number 2, I could see that what I would be calculating is the area under this curve from 0 to 2. Right? So whatever this value is, right, I can just call this generally, I guess, the value of x. And whatever that is I'm kind of imagining that I'm going to be pulling this kind of right bar, if you will, and stretching out this area every time that I change the value of x. That's what this function does. If I change the input, I change where I kind of stop measuring the area. Now, I can take a look at that here on a little applet just to go ahead and kind of illustrate the point further. You'll see here that I have a different sort of a function, and I can see that again I'm starting at a value of 0 and I'm shading the area over to a value of x. But if I was to go to my function g and plug in a different value of x, maybe like 2.5, I can see that I stretch the area. If I plugged in x as a 1, I would only calculate this much area. If I plugged in x as a 4, I would calculate this much area. So on our specific function, which looked like this, I can see that if, again, I selected x as a positive value, I can see that I'm getting an area in the shape of a triangle, and of course it's going to have positive area. Notice if I selected a negative value for x, which is totally possible to do, I'm going to get this negative area back, except for the fact that when I take a look at my integral, then my bounds would be going from 0 to a negative number, And that, of course, would make the area negative again, or multiplied by a -1. And so regardless of which way I go, I end up with a positive total area. So this, again, is a really, really weird sort of function, a type of function that we've never seen before. And we're going to have an interesting goal with this particular function in this section. We want to try to figure out, if we have a function, how do I take derivatives of this function? So I'm going to go ahead and to try to help illustrate how we might determine that, let's at least just think quickly here about, well, how could I possibly maybe write this function a little bit different? So first I'll state this. I can see that g of x is really just meant to calculate the area of this particular triangle. So g of x calculates the area of the red triangle, which has, let me undo that, but this red triangle has a base length of, notice, base length of x, that's how long it is horizontally, and it has a height, actually, of x as well, because remember, whatever I plug in for t is exactly what I get back out. That was my formula for this function. So it also has a height of x. So if I kind of then put all this together, I could really then say that my function g of x, in this specific case, where I'm going from 0 to x of t dt, this is equal to just the area of this triangle. But again, I know how to find the area of a triangle. More generally, just in geometry class, I would say this is 1/2 the base of the triangle times the height of the triangle. Or I could write this as 1/2 x squared. So I actually have a different way of going ahead and actually writing out a function that looks like this. Right? I can easily go ahead and see that in this specific instance, g of x, which has this crazy formula, also has this crazy formula. So again, g of x has a picture, it has a graph. And it's not this graph, because this was a graph of f of t, but g of x's graph would be made by saying I'm going to go ahead and plug in different x's, and the different outputs for g of x are going to correspond to the areas of those different triangles. That's what the g of x calculation is meant to produce. And so what I can see here is that it actually can be found that it has a simple formula of 1/2 x squared. Now the real interesting question here is, do you see an awesome relationship between the function that we were integrating and the formula that we ultimately could obtain here for g of x? Well, you might actually see the following. We can notice here that g prime of x would just be equal to x, and this is the same as the function f of t equals t. Again, just, I guess, assuming we replace replace t with the value of x, right? But these are the same exact looking function, right? I mean, it's just equals x, and this is just equals t. It's a letter difference, but they have the same basic shape. So from this, what we can begin to expect is something really surprising. Interestingly here, when I kind of took the derivative of one of these big, scary integral functions, what I ended up with was really just the formula of the function that I was integrating. It's almost kind of like by taking the derivative, we neutralized the integral. This is the idea of what's summarized in the Fundamental Theorem of Calculus, Part 1. It says, if f is a continuous function on an interval from a to b, like again here I had an f of t function, it was nice and continuous, Then the function g of x, which is one of these big scary integral functions, will have the following properties. First, we can say that the g of x function is going to be continuous on that interval from a to b. It will also be differentiable on the open interval from a to b. And even more importantly, the derivative of g of x is going to be the function f. Just replace all of the t's with x's. This right here is the final derivative rule of Calc 1. This is the last derivative rule, and it's an extremely important one. It says when I want to take the derivative of an integral function thing, essentially what I can do is I can take this upper bound of x, I can drop it in place of the value of t, and then I can effectively erase everything else and just be left with f of x. So this is a very strange derivative rule, and we don't really know why it's working. So in the next video, we'll take a look at how can we actually justify this very strange fact for any function g of x set up in this particular way.